5.7. It's also called coaxial circles.
Wow.
But now we have to sort of know a little bit about inversion, okay? So we'll kind of remind you as it's needed. Okay. Okay, so this is kind of cool. So what it says in the book, okay, like let's just kind of go with it and see what if the book says the same thing. Okay, so you have the coaxial circles we had before, right? So you have like circles, yeah. They all have like center on this line, yeah. Okay, and you take a point here, right? And you draw a tangent to the circle, yeah? Okay. You remember that the tangent has length equal to the power, like the square of the tangent is equal to the power. So this is the root of the power, yeah?
Yeah.
Root of the power? Yeah, so that's b, that's b squared minus c, yeah? Okay. So because it's got the same power, right? All the tangents are the same length. Yeah? Huh? Yeah. They all line a circle. Yeah? Okay.
Wait, how will you get like up to the top of it? Like, is it like the same section? Like,
Oh, there's more on this side.
like how do you get to like the point where it's just like on the y-axis?
Oh.
Because then how like it can't be tangent and it's like coming from within the circle.
Is this one that causes for the y-axis
Yeah, right.
Oh, so it's like a limiting thing, right? It's kind of like you got the whole circle except for the like 2 points.
Oh yeah.
Yeah, I think they talk about that a bit. So you basically have a circle. Well, they lie on a circle, right? But not every point on the circle is on tangent to something, yeah? Because it doesn't touch it, yeah? Okay, so you have this circle. Ah, so clever. I like smart people. So, okay, so the word orthogonal, okay? So basically, we have this thing, if two things intersect, like two straight lines intersect, they make an angle, right? If a circle intersects a circle, the point of intersection, we take the two tangent points, the two tangent lines, and we use that angle to say the angle of intersection, right?
Wait. So like,
Yeah.
No, that's the
Wait, what?
The two lines these
oh,
Yeah, so basically, yeah, so orthogonal just means 90 degrees. So two circles are at 90 degrees if the points where they intersect have tangents meeting at 90 degrees. Okay? So let's see that these are orthogonal, okay? Yeah, I mean the point of orthogonal is that the tangent is orthogonal to the radius, right? Yeah. So basically, for circles to be orthogonal, is like one of the tangents goes through the center of the other circle. Does that make sense? So like if you look at this circle here, this tangent, yeah, is meant to be orthogonal to this tangent, yeah. Okay, but the radius is orthogonal to that tangent, and this tangent is the radius. Does that make sense?
I'll proving the small one is orthogonal to the big one, right?
Yeah.
Oh.
But it's vice versa, yeah. So this circle here is orthogonal to the whole pencil.
The whole pencil.
It's orthogonal to the whole pencil. See, if I didn't have that word, what would I be saying? To all of those
Sets of
coaxial circles?
Anything.
Yeah, pencil kicks ass. Okay.
Does that even
Yeah. Oh, by the way, the significance of orthogonal circles is that they're the ones that when you do inversion, like if you have a circle, do you read the definition? You're inverting about a circle.
I don't even know if we can write chapter.
Oh, okay, but anyway, so inversion is basically you have a circle, you fix a circle in inversion, right? And you basically have this formula for telling you like where to map points.
Yeah.
So like the things inside, the things inside the circle go outside the circle somewhere. Okay, and it's on the same ray to the center,
Yeah.
and it satisfies this. So if the circle has radius r, right? Then this is center O. Then OP times OP prime equals r squared. Yeah. That's the definition of inversion. So it maps P to P prime and P prime to P. Okay? And so we did this thing before, so you might have to look it up at some point. But basically what it says is that orthogonal circles to the inverting circle are exactly the circles that get inverted to themselves. Does that make sense? So like if you had a circle like here or something, right?
Yeah.
And it's orthogonal, then all the points
Can
end up going onto the yeah. Okay. Okay, are we good? Let me just check the chat for a second. The chat has no activity. Does he have Brawl Stars at home? He doesn't have it at home, does he?
I do.
Yeah.
I realize this is showing something.
Oh, Sean says we good. I like that.
Yeah.
Then we're good. Alright, so okay. So can you see now you have like another pencil of circles.
Oh,
Yeah? With lines centered on the y-axis.
yeah.
Yeah?
for each low axis.
Yeah, so basically you have two axes, right? One of them you have a whole bunch of, so this is the plane, okay? So one of them you have a pencil of coaxial circles, yeah? And on the other axes you have a pencil of circles okay? Which are all orthogonal to these coaxial circles. But each one is orthogonal to every single one. Yeah? Okay? And can you see that, but if that's actually the way that they're defined, right? Like if that's the formula for those circles, then they're coaxial as well, right? So like, so there's something about like stuff like this is kind of just like pure coolness. Like there's just no, like you don't need a reason for like, you know what I mean? It's not like, oh, okay, we're doing this to prepare for this exam like 3 weeks ago, right? It's like, this is just, like when you hear it, you're like, oh, that's just cool. That's just cool for like its own intrinsic coolness value. You know what I mean? Okay, so what's the claim, I guess? So, yeah. So basically you have two pencils of coaxial circles, right? Where the line joining the centers is the other pencil's radical axis. Yeah?
Oh,
Yeah.
yeah.
And and they're all orthogonal to each other. Every circle in one pencil is orthogonal to every circle in the other one. So you can smell a bit of an inversive definition coming up. But even before that, I guess maybe we should check that these two things actually work, yeah? I didn't realize the minus sign for a while. That's kind of what got me when I looked at it. But it's actually a minus C in the other one, yeah? So that actually makes a big difference, okay? I'll explain why, but let's check that this works. So if we have, so obviously the circles in the second family have center the y-axis, right? I mean the point is you can like, it's not dependent on the axis. So like, you have the coaxial circles, right? The orthogonal ones automatically perpendicular, yeah? So then you can define the axes to be the radical axes of the two different perpendicular pencils. Okay? So then when you do, then you can write the equation like this. Okay? Okay, what should we check? So we should check that everything on this is perpendicular, is orthogonal to everything on that, yeah? So let's look at a B, yeah? Of this B. Its radius is that. Yeah, we already did that. And we have to check again.
You just prove that way down two circles are perpendicular.
Okay, so we need we need the radii of those circles. Yeah, so we have, they all have center A, right? No, they don't all have center A. The one you're looking at has center A, right? But they all have the same tangent length. No? But they all have center A as A varies. So the distance between A and B is A squared plus B squared, right? And that's supposed to equal the sum of the radii. Yeah?
Sum of the squares of the radii?
Yeah. Sum of the squares of the radii. So this is A squared minus C, right? Plus B squared minus B squared. Yeah. Where's the 9 degrees? It's here, right? Oh, okay. So it's this length here, A squared plus B squared, right? Should equal one of the radii. Oh wait, what am I doing? This is plus the other radii squared. And this.
So if you put A squared plus C plus B squared minus C, and then
Yeah. Alright, so what's the radii here? It's B squared plus C, right? Yeah. Why did I write B squared minus C? Yeah, I guess we calculated the power before it's B squared minus C. Yeah. Maybe that we did something wrong. Did we do something wrong before? What was the power of B? Yeah. I'm gonna try. The power of B was. So it's D squared minus A squared, right? So it's A squared plus B squared minus A squared minus C, yeah? That should have been a plus C. That's a minus C in that whole other video that's going to just stay there. You guys have to save me from this kind of embarrassment. It's your job. It's your job. Okay. That's B squared plus C, right?
Okay.
It's b squared plus c. So that works, yeah? Yeah.
Yeah, because that was plus
Mm-hmm. Yeah. And then I think there's only one circle for each center, right? That has that property. Because it has to have the radius equal to the powers, right?
Yeah, because the vertical axis is the same.
Yeah. So these are the pencils, yeah? Okay, so now let's get ready for some verbalness. Okay, let's see if we missed anything. So in section 2.3, we saw that any two non-concentric circles, alpha and beta, belong to a pencil called alpha-beta of coaxial circles, such that the radical axis of alpha and beta is also the radical axis of any two circles belonging to the pencil. Any point P on the radical axis has equal powers with respect to all the circles in the pencil. Whenever the power is positive, blah, blah, blah. Yeah, so it goes through the cases, yeah? Yeah. I seem to think the power was C, yeah? Oh, actually, this is what I want to talk about. So the power was, what's the power, actually? It's, the power of what? Oh, yeah. The power is B squared plus C, right? Power split power. Yeah. Okay, but I guess remember the last time we did it, we had the C, and the C told us what the case was in, right? You remember I was saying non-intersecting, yeah? So when C is negative, that's when it's when C is when C is positive, it's non-intersecting for the top one, right? Yeah. But since the signs are switched, it means when one is non-intersecting, then the other one's intersecting. Right? So that's kind of interesting. So when one of them is like this, then the other one's like that. It cuts the x-axis. Yeah. And if one of them's tangent, then they're both tangent. Yeah. Let's C equals 0. Yeah, I think it says that in more or less. Okay. So they're called complementary pencils of orthogonal circles. Yeah. So they use gamma and delta, and then alpha and beta. Yeah, so you can't just define it to be orthogonal to one circle. It has to be, you have to have two different circles, and then it's orthogonal to all of them, right? I think if you have just one, because I guess when you have two, it gives you a radical axis, right? If you have just one, you could be orthogonal anywhere. Yeah. Okay. Yeah, and then they write down the two equations. A and B vary while C is fixed, right? Okay. So if C is greater than 0, the first pencil consists of non-intersecting circles, and the second consists of intersecting circles, all passing through the limiting points. So the limiting points are called plus or minus root C, yeah? So that's like here and here, yeah? Which may be regarded as degenerate members of the pencil.
Oh, like this one.
1 point circles, yeah? Yeah, I guess you can't get circles that go past that point. Oh. Yeah, so A has to be outside. A has to be outside. Is it outside or inside? It should be outside. Yeah, that doesn't work. So you have A squared minus, C is positive, negative. A squared minus C can't be negative, yeah?
one. A is
Yeah.
less.
Yeah, so when C is positive, that's when it has a chance of being negative. Okay. Finally, if C equals 0, we have two orthogonal pencils of tangent circles all touching one of the axes of the origin. The members of a non-intersecting pencil of coaxial circles occur in a natural order. Okay, this is interesting. The members. So now we're starting to get to inversion. Okay, so the members of a non-intersecting pencil of circles occur in a natural order determined by the order of the points in which they meet the line segment joining the limiting points. Huh? What does that mean? So the non-intersecting. Okay, so the members of a non-intersecting pencil of coaxial circles, yeah, occur in a natural order determined by the order of the points in which they meet the line segment joining the limiting points. Yeah, so hold on. Yeah, so the centers are getting close to it.
Yeah.
So the actual circle will hit it, yeah?
There's one segment there, not one.
Yeah, so line segment, I guess, is here, right?
Yeah. Wait, can you make the circle big enough that oh no, it's not.
So it's kind of saying, like, I guess you have these circles, right? So that's talking about those black circles there, right? So the members of a non-intersecting pencil of coaxial circles occur in a natural order determined by the order of the points in which they meet the line segment joining the limiting points. So I think this is like a 1, 2, 3 kind of thing, yeah?
Yeah, the one's closer to the same time.
This natural order enables us to say precisely which one of three members lies between the other two. Huh?
Can you say the same thing about the specific radius?
No, they have different centers.
But they're not intersecting anywhere, right? So
Oh yeah, you're saying that where they're nested, you mean?
yeah, right.
Yeah. Well, I guess, but yeah, I guess they all have to be inside each other, yeah? Wait, so is it clear that every one of the circles intersects the segment? So that would mean,
Yeah, they can't go past that, right?
yeah. So is the radius always long enough? So, so the radius is equal to root a squared minus c, right? And we need the center minus the radius. So we need a minus root a squared minus c to be less than root c. Or in other words, root c plus the radius is bigger than a. square root c plus
This is still b squared with the some
Yeah.
positive.
so it's like root a plus root b is greater than plus b. Root it's a root. Yeah, this is not. What is it we're gonna say?
We are able to square everything. But if we do it again,
Yeah. Yeah, so if you so if you square anything, you get this cross term, right?
Yeah.
That makes it bigger than just a. Yeah. Okay. 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 Now, this is where you're starting to get back. You're getting to be on your own soon. Okay. We may describe the pencil alpha beta inversively. Okay. I guess this is alpha beta. Alpha beta inversively as consisting of all the circles orthogonal to gamma and delta so all the circles orthogonal to gamma and delta, and the pencil gamma delta to consisting all the circles orthogonal to alpha and beta. So in other words, alpha beta consists of all circles orthogonal to any two circles orthogonal to alpha and beta. Huh? Remember we said that the orthogonal can be anywhere, right? We need a radical axis, so we need two. Yeah, so I guess the point of saying that is to say it without reference to gamma delta, right? So you have alpha beta, yeah? You have two circles, okay? Then you find, we had an exercise with that, remember? You could find the X circle orthogonal to two circles, right? Yeah? So you have a circle, but then we know how to kind of do it anyway. So we have a circle, two circles orthogonal, yeah? But they're not the same. And then we have all the circles orthogonal to those two. And that's the pencil alpha beta. Yeah? So I guess that's inversive because it only uses the word orthogonal. And that has a meaning that's specific to inversion, yeah? Okay. Now erase some stuff. Erase some stuff. So it's funny, I was looking at some of the stats for the YouTube. It's like no one can watch these videos for more than like a minute. Yeah. I need what's the opposite of clickbait. Like I need to like have a title that tells you exactly what you're in for and what's expected. And so you just don't even click on it. But every click will have like 2-hour view duration. It's just non-exist.
There's only one.
One view is for myself.
Yeah.
Accidentally left it on. Okay. So we have two intersecting circles. Let's call this gamma and delta. So this is a diagram in their thing. I haven't quite finished drawing it, but it might come in handy. Okay, and intersect at P and O and P. Okay. Yeah. So if O and P are the common points of two intersecting circles, gamma and delta, yeah? The inversion of any circle with center O, the inversion in any circle with center O yields two lines through P prime, which is the inverse of P. Okay. Yeah, but this sentence didn't really make too much sense to me. I think what it's trying to say is, okay, so you're trying to invert about O, right? So P prime will be like either here or maybe somewhere over there, yeah? Okay. And I think it doesn't say explicitly, but I think what we're trying to do is we're inverting gamma and delta. Yeah, the circles. Okay. So first of all, you know that circles that go through the center of the inversion circle turn into lines, straight lines. So basically there's this interesting thing where like if you invert a circle that passes through the center of the circle you're inverting with, right? Then the image of that circle will be a straight line. Okay? And so both of these circles will satisfy that. Yeah? So they'll both be straight lines. And both of them have a common point P, right? So they're going to have a common point P prime in their image. Okay?
Oh, so that has to be.
Yeah, so the image will look like this, like P prime. And there'll be like two lines that goes through P prime. Yeah? And I'll call it maybe like this would be gamma prime, this would be delta prime. Yeah? Okay. Okay. And the pencil. Oh, so the circles orthogonal to these lines, okay? These two lines are a pencil of concentric circles with center P prime.
Circles. Orthogonal to both lines.
Yeah.
Oh.
So can you see that a circle that's orthogonal to one of the lines, right, has to have center that lies on one of the lines. Yeah? Because you have a circle that's orthogonal, yeah? Then that has to be a radius. Right? So for the other line, it's the same thing. So then it has to lie on the intersection. That's the center of the circle. Yeah? So this has like a... Yeah? Draw another one. Just in case you don't know what concentric means. So these are the pencil of concentric circles that are orthogonal. So orthogonal to both delta prime and gamma prime. Yeah. Alright, I'll check the chapter. Oh, being said, shouldn't the radius be b squared plus c root? Oh, yeah. So he picked up on it. We should have checked the chat more often. I need some technology, like this chat's just on the screen. Yeah. We'll get there. Alright. What is it? Okay, so the pencil gamma delta inverts into the diameters of these concentric circles. What does that mean? The pencil gamma delta inverts into the diameters of these concentric circles. Yeah, so we have these pencil of orthogonal circles, these things, yeah?
Yeah.
Okay.
What do we need?
The pencil gamma delta.
So
So yeah, itself, right? So
it inverts itself into a diameter.
well, it does that, right? See?
What
But the pencil, what's the pencil?
all diameters.
What's the pencil of gamma delta?
So is that all the circles?
Yeah, so all the ones are coaxial with gamma delta, right? So gamma delta going to these lines that go through the center. So I guess what we mean by diameter is a line that goes through the center, yeah? Because we know they go to lines.
Yeah.
Or do we? Well, they're not going to segments. We know for a fact, so for inversion, yeah? Circles either go to straight lines or circles. The circles that pass through the origin go through the straight lines. Circles that don't pass the origin go to circles. Yeah? You're going to assume that for this. Okay. So the fact that it's claiming that they're going to diameters, right, suggests that it's going to go to straight lines, yeah? So that suggests that the circles pass through the origin, right? Yeah, so I guess this is the thing. Like if you don't know what the circles are, this could help you figure it out, right? So the circles have to pass through the origin, right?
And all the circles are reflected.
They're the pencil of gamma delta.
Is that not just resonance?
Yeah, so basically, yeah, exactly what does it mean, right? So it has to be some circles that pass through O, yeah?
Yeah. That's right.
O is one of the intersection points of gamma and delta. Yeah?
Oh, before we
Yeah, and then we inverted about it.
I don't know.
Yeah, so I guess, yeah, figuring out what pencil delta gamma delta means, yeah? So pencil means that it's all the circles coaxial with gamma delta, right? So they all intersect O and P, yeah? Okay? So of course, they all intersect O means that they're all straight lines. Yeah? They all intersect P means they're diameters. Yeah? Yeah. So this is like reading this book is probably the most epic definition chase ever. Okay? Because you really just definition chase all the way to the end. Does that make sense?
Yes.
Yeah.
So the pencil go to these other lines. You can draw some other lines in there. Yeah? Members of pencil. Gamma delta. Yeah. Just a generic member. Member number 86.57. That doesn't make sense. Alright.
Why is this sentence kind of at the end of the page? This is hence.
Hence. Oh yeah, because they always say like the proofs before the theorems. It's like, hence we proved this without telling you that's what we're trying to do.
Oh, wait, so that's true.
But in some ways, it's kind of like it's trying to maybe pretend if it's not working out, but actually trying to be like natural. It's like we're just proceeding naturally, and the theorems are just falling as we go. You know, like we didn't know that was the theorem that we needed. This is all we could do, and this is what we got. Okay, it's kind of nice sometimes. It's like what theorem did you just prove? Well, State your favorite theorem. Alright, let's see if the chat has any objections. Howls of outrage. No, nothing. Maybe I should log into Brawl Stars to see if Sean and Having are playing at the same time.
Yes.
Alright. Oh, I got a reply on the chat. Interaction. Nah, I'm not on. I don't know about high being, but I'm not.
Yes, of course.
Yeah. Yeah, it's good because if you say someone else is, you have to be on to know.
Yeah.
It's like, alright, so we're all good then, I'm assuming. Alright, what's the next claim? The same figure, what? The circles orthogonal to these lines are a pencil of concentric circles and a B prime, yeah? Okay. The same figure can be derived for any two non-intersecting circles, alpha and beta. Okay, so this is where this diagram comes in. We have alpha and beta. Okay, that's alpha and beta's on the other side. Okay. The same figure can be derived from any two non-intersecting circles, alpha and beta. For we can easily find gamma and delta in this figure, which are intersecting and orthogonal to both alpha and beta. Namely, two circles with suitable radii whose centers lie on the radical axis of alpha and beta. Yeah?
Yeah.
So what's the, I guess now we know the claim, we'll know the claim now, so this is theorem 5.72. Theorem 5.721. Any two non-intersecting circles can be inverted into concentric circles. Any two non-intersecting circles can be inverted into concentric circles. Huh? Okay, so let's say, so the non-intersecting circles would be alpha and beta, yeah? Okay, so if you have two non-intersecting circles, you find gamma and delta that intersect that are orthogonal to both. Yeah? And then what can you do? Okay, then you invert with respect to O. Yeah? Yeah, that gives you the concentric circles, right? Because those alpha and beta have to be orthogonal to the images of gamma and delta, yeah? Does it actually say much more than that? If you have two non-intersecting circles, So if you have any family of non-intersecting coaxial circles, you can invert them into concentric circles.
Yeah.
Is that right?
Yeah.
Should I state theorem 5.72 before it's due? So there's another. Okay. They only state at the bottom, yeah. Theorem 5.72, yeah. And we'll wonder about it when we get up to it, but I'll state it. Any two circles. So if you remember last week, this might be more motivating. Any two circles have at least one mid-circle. Mid-circle, yeah. So mid-circle is a circle, think of inversion. So the circle you invert to. So a mid-circle is something which you invert about to get the other two circles into each other. Yeah? Any two circles have at least one mid-circle. That's what we got stuck on, what mid-circle was, yeah? Have at least one mid-circle. Two non-intersecting circles or tangent circles have just one mid-circle. Two intersecting circles have two mid-circles. Remember we were saying they had two mid-circles? That was like the thing.
Circle of anti-symmetry.
The two intersecting, if they intersect, okay, so if they intersect, there's just one, there's two, okay, and otherwise, if it's tangent or tangent, yeah, there's only one.
Yeah.
Yeah? Okay, we'll store that for it. Okay. Alright, so after 5.71, for this purpose, the circle of inversion may be any circle whose center is either of the limiting points O and P. Yeah. Of the non-intersecting pencil alpha beta. Oh. So you take the limiting points of, so if you want to do it without getting the other circle, you know the center is the limiting point of, yeah, it's like the root C. O and P, yeah?
Yeah. Wait, is it
No. The O and P are the x-intercepts, right? So they're like root plus or minus root C, yeah?
Yeah.
So you can take them to be the limiting points of yeah, remember we said the limiting points were plus or minus root C.
Yeah.
Yeah. Was it obvious we could get those circles? I suppose, yeah. Because we had this family, right? We had the whole family. Not just those ones, we had the whole family. Okay, so for this purpose, the circle of inversion may be any circle whose center of the limiting points O and P of the non-intersecting pencil alpha beta. If alpha precedes beta in the natural order from O to P, okay. Any circle with center O or P will invert alpha into the larger or smaller of the concentric circles.
Larger or smaller.
Oh, sorry, there was with center O and then all P in brackets, we'll invert alpha into the larger, like all smaller.
Oh.
Oh, okay, so the natural ordering of these circles touching the segment is preserved by the concentric ordering of the circles. Yeah?
Calculus introductions are to
Yeah.
the sentence.
No, look on the right.
Yeah. Yeah, and I guess, the points closer to O will have to be further away from O
Yeah.
when you invert, right?
Yeah.
Okay. By changing the radius of the circle of inversion without moving its center, so keeping the center O without even changing the radius, replace the pair of concentric circles by another pair whose radii are in the same ratio. What? For the new inversion is equivalent to the old inversion followed by a suitable dilation. By inverting in a circle with center P instead of O, we replace the pair of concentric circles by another pair whose radii are in reciprocal ratio. Some advanced stuff here. If alpha and omega are any two distinct circles, the inverse of alpha in omega belongs to the pencil alpha omega. For any two circles orthogonal to both alpha and omega invert into themselves. If alpha inverts into beta, we call omega a mid-circle of alpha and beta. This seems more natural than the classical name circle of anti-similitude. Since beta belongs to the pencil A omega, alpha omega, omega belongs to the pencil alpha beta. We are now ready to prove the converse of theorem 5.45. Oh, what was theorem 5.45? Maybe that's the one I should have written up. But I guess it's the converse of what I wrote up.
The inverse of any circle is a circle. That's the theorem.
Oh, what?
Yeah.
The inverse of any circle is a circle.
Wow.
Well, it's redefined. Well, yeah, it's redefined the line to be a circle that kind of meets at the other end of the other end of the earth. Yeah, like it wraps around the sphere, and meets again. A geodesic. Okay, so by changing the radius it's just saying that if you change the circle of inversion, right, you get still concentric circles, but the ratios, the radiuses are different, but the ratios are the same. Yeah. And it's saying if you change the radii of the other one, yeah, then the ratios are not the same, but like the reciprocals are the same. We can verify that. So the new inversion is equivalent to the old inversion by suitable dilation. Okay. By inverting in a circle with center P instead of O, we replace the pair of concentric circles by another pair whose radii. Oh, so if you have two concentric circles, right, that you'd gotten by inverting from O, right? If you switch to P, you get another pair of concentric circles, but the radii have a different relationship. Yeah?
Yeah.
Yeah, I feel like there's some kind of reflection going on. Does that make sense? So the claim that we're trying to verify now, right, is so we're inverting by O, but we've fixed the radius, yeah? If we remove that radius and switch to another radius, yeah? Like if we pick two circles, like 1 and 2, yeah? They no longer be the same circles. They'd be something else, yeah? But so these circles are purely defined by their radii, right? Because we know that the center is P prime still, yeah? So these two radii will be replaced by another two radii, yeah? But the radii are in the same ratio, as we're saying. So R1, I don't think it actually says in the book, but I think R1 on R2 is equal to R1 prime on R2 prime. That's what it's trying to say. Yeah? Does that make sense? What do we know about the radii of the circle? Okay, let me write down the other thing. Yeah, and if you replace O by P and you invert it here, right? We call it R double prime. I think it's saying that R1 on R2 is equal to R2 double prime on R1. Yeah, the double prime is the P. So I guess you remember this reciprocation hasn't happened yet in this book at this point. Yeah? This is only 5.7. Well, so the book actually gives you an explanation of why it's in the same ratio. So it says that by changing the radius of the inversion circle is equivalent. So the new inversion is equivalent to the old inversion followed by a suitable dilation.
Yeah.
Does that make sense?
We got that. Reciprocation.
Oh, okay. So you got the first one then.
Yeah.
So how does that work? So you have
Because like basically the points times y and their is r squared, right? And then if you change r, say r prime squared or something. Yeah. And then that means the ratio will also be changed by like
Oh,
some
okay. So you're saying
r prime
so I guess OP times OP prime is equal to R. Yeah.
Change that to something else from the square. And that means
And then what do we have? So the radius. How do we get the radius of the concentric circle? Yeah. So if you have OP, so OP1 and the OP1 is R1, yeah? And you're saying OP2 times OP2 prime is R2 prime, yeah?
Yeah, this is like one side to
Yeah, so I made the subscripts. I guess the P should be the same, no matter what. The P is the same for that.
yeah.
But then the OP1 prime and OP2 prime are given by different radius of inversion. How does that work? So,
So the inversion and OP is constant. So we can
so you're saying
lump that all together.
so it's saying any inversion, right? So like not just for P, but for like any point whatsoever. So like S, yeah? OS OS1 prime equals R1 squared, and then OS2 and OS2 prime equals R2 squared, yeah?
But is that also the same?
Oh yeah. This is the actual put stuff with P, I guess. So the S is the same, yeah? So are we just getting to S1 prime and then dilating it? What does dilating mean again? It's dilating about O, right?
Yeah. Yeah, so
What's the dilation?
so it's like would be OS1 prime equals R squared on OS, and OS2 prime is to R2 squared on OS.
Oh,
And this ratio into R2 squared and OS squared.
it actually kind of makes sense, huh?
Yeah.
So the overall change is the dilation of the first inversion. Yeah. So then the concentric circle should all just be enlarged or shrunk accordingly. Yeah. I believe that.
Yeah.
Any objections from the chat? It's like so unrigorous. Wait, no, he didn't say anything. Are we going to do exercises on these? I think we can, yeah. Yeah, so we are going to do the exercises at some point, yeah? And I found some problems, which might be interesting. But I think to be fair to the problems and the exercises, the problems, especially the problems, they need to be tried first. They can't just be like, answer the problem. You didn't even know what the problem was. It's like trivial. It's like, the answer is P equals Q. That's just it. They were never different. They're actually the same thing. Okay, so I guess we were convinced by the dilation argument. You know? Okay, what's the other one? By inverting in a center P instead of O, we replace the pair of concentric circles by another pair whose radii have a reciprocal ratio. Okay, so if you're inverting about P, yeah, the center of these concentric circles is no longer P prime, yeah? It doesn't even make sense. So it's now O prime. Yes. Reciprocal. Oh. So we kind of know that it's like an inverse relationship because the circles that are on the inside now should be on the outside. Is that kind of clear? So the circles on the innermost concentric circles now will be the outermost concentric circles.
Yeah.
Because the inner ones are the ones that were closest,
Closest to
sort of like closest to P, yeah? Or at least they were the farthest from O. Yeah?
closest to
And the ones that are closest to O,
closest to O means further out.
yeah. And I guess closest to P is, yeah, it's also because it's closest to the center point, right? The ones outside of P, yeah. But why are they exactly inverse ratio? Hold on. What does inverse ratio even mean? So it's like, so So if you just inverted the same two circles, right? Yeah? The exact same two circles. So which two circles will we say like 1 and 2 are? Like, are they alpha and beta? Is that what we're doing? Any two non-intersecting circles?
Gamma and delta. Wait, no.
So gamma and delta
No,
gives
no,
you O and
Gamma
P.
and delta give you lines.
Yeah?
Yeah. That's alpha and beta.
So alpha and beta, let's say it's 1 and 2, yeah? If you do it about O, yeah? Yeah?
Yeah.
Now if you do the exact same inversion with the exact same radius, yeah, about P,
Yeah.
would you switch them?
Yeah, probably.
That makes sense, right?
Yeah.
It's completely symmetric.
Oh, yeah.
That makes sense?
Oh, yeah. 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 Okay.
So basically, I guess what I'm saying is, because the ratios are preserved when you invert about O, right? You can actually pick any radius you want. It'll still suffice to show this, right?
Yeah.
So you just pick the same radius for both, right? And as long as you say that those two are reciprocals of each other, then all of them will be reciprocals of each other, right? Because these are all the same ratio, those are all the same ratio.
Yeah.
Yeah? So then you can just pick the same radius for both, right? So maybe it's a reflection. Maybe it's a... How would you say it?
So, isn't it still reciprocation?
Huh?
Isn't it still like when you have R1 and R2 because...
Yeah. So what happens? So if you do reflection O to P, right? Yeah.
Yeah.
That'll change alpha and beta, yeah?
Yeah.
And then you do the inversion about
Yeah.
P, right? So then you should get this with alpha and beta changed. Yeah?
Yeah.
I think that's a proof. Isn't that a proof? Inversion,
Yeah.
reflection. Inversion, it's a conjugation, isn't it? It's a reflection, inversion, reflection.
Yeah.
So how would you say it? So you invert about O, okay? 1 is alpha, 2 is beta, yeah?
Yeah.
Okay? Okay, if you reflect, if you reflect, okay?
Yeah.
So P now goes to O. Alpha is beta and beta goes to alpha, yeah? Oh, actually, this is only the case where the two circles are the same, yeah?
Beta.
So the alpha and the beta are radii as well. That's a bit of a problem.
The same.
Alpha and beta same way.
Yeah.
Although it's two random circles.
Yeah, so I guess if there were two random circles, their reflections wouldn't go to each other.
Yeah. Is that that? Are we still invert around P?
Yeah.
But still do this one and two.
Yeah.
Oh, no, we did.
Um, this is, Hmm. Oh, did we have this thing where the distances are in some kind of ratio? We had that. This is probably where you got that thing from. Yeah, like your idea. This kind of reminds me of this. The cross ratio is preserved, but even before that, well, not before that. Yeah, maybe it's related to this theorem, I think. So we have, let me erase this, yeah? There was this thing we had before where A prime, B prime is equal to, yeah, K squared, so that's the radius, yeah? AB divided by OA times AB. Yeah. So can you see that that's like A double prime, B double prime equals, you know, some other K squared. AB on PA, PB.
What's AB?
Any 2 points.
In the circles?
Anywhere. Anywhere except for O and P. It's just some formula we had from earlier. Yeah. So if O is fixed, right?
Is that a central inversion?
Yeah. So here it's P, yeah? So I think that proves that one too, right? Because if you had, so that's like one radii, right?
Yeah.
And then you had another radii. Like these two will always cancel. So set circle. So the radii here would be P prime something, right? P prime B. P prime B prime. So then that would be a P. A squared PB on OP OB, yeah.
Where do we get A from? So B prime equals to B prime B prime.
Which one?
Like that line there. Yeah.
What do we get? What?
Why is that true? B prime B prime.
Yeah, I just let A equal P.
Okay.
I want. Oh, that's not right. No, that's not right. Yes, because the radii doesn't necessarily invert to the radii, yeah?
Yeah.
Because the center doesn't necessarily go to the center. Oh, but hold on, we do know the length. Oh, but we're talking about the length of it, yeah?
Yeah.
So P prime. So if you just pick any point B that inverts into this, any point on this circle inverts to there, right? So you just need a point B on this circle, yeah? Then the length is the radii, yeah?
Yeah.
That's P prime B prime. That's the radii, yeah? And so you just need the distance. So yeah, so it's not the radii, but it's like some fixed distances with the radius, yeah? Yeah?
Is P the center of the range or is it still
It's still over that top one, yeah? So if you pick another point C or something, right? For another circle, yeah? So B for one, for B for out, or maybe you have like PC prime equals K squared PC on OP times OC, yeah? P prime, C prime. So dividing these two will give you the ratio of the two radii, right?
Yeah.
Right?
So K squared over B cancels.
Yeah, and the point is the K squared cancels. Yeah? So it doesn't depend on the radius inversion.
Yeah. Oh.
Yeah?
Yeah.
So this is promising to prove the first claim. Yeah? So the ratio of the radii, yeah? Like if you assume this formula is true. So you know what this formula is saying. So if you take any 2 points, right? The new length after they inverted, right? The distance between the images is equal to the old length times some factors. Yeah? So here we see the k squareds cancel, right? So the ratio of the radii don't change. So that's the proof now. For this, maybe we can say something like, what happens here? Okay, so we want to invert about p now, right? So we change these to p's. We don't care about the radii that much. And now we want the o's to be a double prime, right? Yeah. So we want a double prime to be. We want the radii now for the other circles, right?
Yeah.
So the radii now is centered around. So the center of these circles is now O prime. Yeah. No, we'll call O double prime. Yeah. D double prime equals K1 squared OB. Yeah. On PA, PB. Yeah?
It's a PA.
Yeah. Good. Okay.
And that cancels with basically PB on OB times OB.
Yeah. So,
Oh, it does.
does it?
Yeah.
Oh.
Well, if you reciprocate it.
Yeah. Yeah, okay. So then you get O double prime, B double prime, yeah? On O double prime, C double prime, yeah? Because we're on the ratio of the radii.
Isn't this something that we're comparing it with like when we invented it around?
Yeah. So I think this will work.
Okay.
So that's what you get for the B, right?
Yep.
Do the same for the C, and then ratio them, yeah? Okay. Once you do the ratio, this K square will cancel, right?
Yeah.
And then the OP will cancel, yeah? So you just get OB on PB, yeah? Right? Oh, oops, yeah. Oh. Yeah, so PB OC, yeah? And then this is PC, yeah?
Or you do the same.
And then do the same here, right?
Oh, yeah.
So the ratio here, you get, so the ratio P prime B prime, yeah? On P prime C prime, yeah?
Oh, that's the same.
Are they expecting us to see it like this or something else? This feels a little bit harder than the standard definition chasing. But it does make you learn the formula, which is a theorem in the book, yeah? It's the P prime, C prime.
Yeah, the same stuff cancels.
It's the same stuff cancels, and then you have PB on OB, right? PB on OB, and then it's PC on OC, yeah? They're reciprocals of each other. And that's the point.
Yeah.
Yeah? That's a proof.
Yeah.
Yeah, well, we'll give the credit to them anyway. Because they must have meant something like this. But they didn't. Maybe it was even more obvious than this. But you can't be more sure than this, that this is right.
Yeah.
Alright, so are we at the point of saying this? We're almost finished the theorem. Oh, gotta get this as a theorem. Get the theorem. Get the theorem. Well, the theorem's been stated, so it's not like gonna just jump out at you. Okay. Alright, let me ask the audience. Oh, sick reciprocals. Yeah, O and P are just the intersections of delta and gamma. So there might be an easier way to do it but I guess this reviews that theorem. This is like one of the very first theorems in the chapter. You might even want to prove it as an exercise. You know, just like using the definition of inversion, yeah?
So isn't it just that green bit?
Yeah.
Oh.
So just divide stuff. So I guess in a sense that's why it was the same as that green bit, because you used the green bit to show it before, right?
Yeah.
So it's the same, but sort of.
Well, similar.
It's kind of like a formula where the subject is what you need to solve the problem, versus a formula where like stuff is just left and right.
Yeah.
Been in a chair for 3 hours. Yes. For some reason, yeah, like sitting on the ground is starting to hurt. Does this mean you're old? Because I remember when you were in school, we just sat on the ground for like all of primary school. Wait, did you sit on the ground in high school? Nah. You rock back on the chair and lean against the wall, right? Okay, let's try and finish this before the computer dies. Okay. If alpha and omega are any two distinct circles, the inverse of alpha in omega belongs to the pencil alpha omega. Does it make you feel stupid when you hear this kind of stuff? It's just like, yeah, I don't even know what it's saying. Or maybe it's like you know that it's saying something too precise for you to handle at the moment. Like it's maybe not just you don't know what it's saying, you know that it's saying something that you don't want to hear right now. So if alpha and omega are any two distinct circles, so let's say beta, yeah?
Yeah.
The inverse of alpha, so if you invert one with respect to the other, yeah?
Oh, it's also in the pencil.
It's also in the pencil.
Okay.
Does that make sense?
Yeah.
Because, why is that? Okay, it actually tells you, for any two circles orthogonal to both alpha and omega, invert into themselves. No, this is defining the circle of omega. So for any two circles orthogonal to both alpha and omega, yeah? Both alpha and omega. Oh, okay, so there's a symmetry between alpha and omega then. Okay, so alpha, so if something's orthogonal to alpha, right, then if you invert it about alpha, it'll invert to itself, yeah? That's the point of orthogonality, yeah? And that circle we said is also orthogonal to beta, yeah? I mean, to omega. So if you invert it about omega, it also goes to itself, okay? So if alpha inverts into beta, but is that finished? So we're still, okay, is it clear? If alpha and omega are any two distinct circles, the inverse of alpha in omega belongs to the pencil alpha omega. The inverse of omega. Okay, so the inverse of omega is orthogonal. So like, okay, you have alpha, right? Let's say beta is omega, yeah? And there's gamma, yeah? So the inverse of gamma with respect to alpha is itself. Yeah? The inverse of omega, this omega, yeah, which is beta, with respect to alpha, is orthogonal to the inverse of gamma, yeah? So inversion preserves angles.
Yeah.
So it preserves orthogonality. Okay? So then it's orthogonal to gamma, right? That makes sense?
Yeah.
So the inverse of beta with respect to alpha, or the inverse of omega with respect to alpha, is orthogonal to gamma. Okay?
Also, it's on the pencil.
Yeah, and it's also orthogonal to delta, yeah?
Yeah.
So it's on the pencil.
Oh. Okay.
Yeah?
Yeah.
So the inversion of any member of the pencil with respect to another is also in the pencil. Well, anyway, the pencil is inversion closed. No, I didn't. The book didn't say that, but that's what it sounds like from my education. It's closed under inversions with respect to each other's. That's such an abusive maths. I'm sorry. Okay. if alpha inverts into beta, okay,
Yeah.
we call omega a mid-circle of alpha and beta. Yeah, so if the circle of inversion takes one circle to another, then those two circles have the circle inversion as a mid-circle. Yeah? This seems more natural than the classical name. It should be than the classical name. This seems more natural than the classical name. Circle of anti-similitude.
Yeah.
Holy crap.
Why are you names like
It's like the name is purely to distinguish it from other things that are named, as opposed to for convenience of naming stuff. It's like, to say that, you might as well just describe it explicitly, you know?
It's like the circle.
The circle of anti-similitude. Stop, okay.
Yes.
Or it's like, yeah. Or like, the circle which inverts one to the other.
Good name.
Mid-circle.
Yeah.
Yeah, so obviously they value the sort of notation reducing exposition kind of value,
Yes.
as opposed to the descriptiveness value. Okay. Since beta belongs to the pencil alpha omega, omega belongs to the pencil alpha beta. Yeah.
Oh.
Wow.
We are now ready to prove the converse of 5.45. Oh, okay, so the theorem 5.45 was
A circle.
any circle, if you invert it,
Yes.
it goes to a circle, yeah?
Yeah.
It's
What's the converse?
Converse.
It's a circle.
The inverse. We have to say inverse
Oh,
in this
yeah.
situation. The inverse has a meaning in logic too.
Yeah.
Inverse is like A implies B, the inverse is like not A implies not B.
It's contrapositive, isn't
Contrapositive is not B implies not A.
Oh, well, I thought that was. Oh.
The converse is B implies A.
it? Isn't not implies not the third converse?
Yeah, it's equivalent. It's called the inverse.
Wait,
I think, anyway. I only heard this term recently.
Okay.
A implies
Oh.
B. A
Alright.
implies B means not B implies not A, right? They're
Yeah.
equivalent.
Yeah,
Yeah,
so
so then
the
the opposite of it.
contrapositive is equivalent, yeah. Alright,
Oh.
so any two circles have at least one mid-circle. Two non... Wait, so if the inverse of a circle is a circle, is the converse of that saying any two circles can be inverted into each other? So how do you turn it into an if then? How do you turn it into an if then? So if it's a circle,
If the circle exists,
then the inversion is a circle.
that would be the exact same.
If it's inversion, it's a circle.
So
It was inverted from a circle.
Oh,
Yeah.
It was a circle.
Yeah.
Nice.
Does that even mean the same thing?
wait, if it's a circle, then the image is a circle.
Yeah.
If the image is a circle, then
Maybe the not image was a circle.
no, it can't be that because that's just symmetric.
It's like if and only if. Not like
Yeah, you have to put the if in a way that's not symmetric to the only if. So two circles
Isn't it just different numbers?
invert
It's
to
with
each
something
other.
and its converse. That's just different. So it's speaking of kind
But what is the converse?
If a circle inverts to circle implies circle
What's
is
the opposite
inverted
of
from
inverse?
So if you have if you have a circle and another circle, you have two circles, then you can invert one with respect to the other into a third circle. Yeah.
Yeah.
Okay.
So if you can invert,
Oh, but actually.
1, if you have,
If one can be inverted from one intersect to another,
yeah,
then
you have two circles. Yeah. Yeah, okay, so if, okay, so think about the statement we're trying to say. So it's like if you have two circles, right? Yeah? Then you can invert. So if you have two circles, then you can invert from one to the other. Yeah?
yeah,
Okay. So the converse is like if you can invert from one to the other, then you have two circles. Right? Yeah. So the other one was like if you had two things that inverted to each other, right?
Oh.
One of them's a circle, then the other one's a circle.
yeah.
This one's like,
If you have two sets, like
yeah, so if one of them's a circle, then two of them are circles, yeah?
yeah.
This one is like if you have two circles, then one of them's a circle, and they invert to each other,
Yeah, okay.
yeah?
Okay.
Yeah, so if you have two things that invert to each other and one of them's a circle,
Yeah.
then both of them are circles,
Yeah.
yeah?
Yeah.
And so the converse here would be, if you have two circles,
Yeah.
Yeah.
then one of them is a circle, and they invert to each other.
Yeah.
Okay. That's cool.
Yeah. Okay. Like it feels like what we've just done can turn anything into the converse of anything. It's like the kind of feeling you get after that kind of wizardry. All right. Okay, so can we invert any circle into any other circle? Since beta belongs to the pencil. Oh, that's kind of crazy. So if you just take two circles, right?
Yeah.
Alright, if you take any two circles and take their pencil, right?
Yeah, there's a circle on the pencil.
There's a circle.
On, yeah.
So if you take two circles on a pencil, so it's clear that you get another circle on the pencil, yeah?
Yeah.
And any circle on the pencil is gotten that way, right?
Yeah.
Oh, yeah.
Yeah, by inverting intersect or
Yeah.
So that's true. Right?
But hold on, but how do we know how to get from any one to any other one?
Any circle to any other circle.
with respect to any circle.
Since beta belongs to pencil alpha omega, omega belongs to pencil alpha beta. Oh. That makes sense. Omega belongs, yeah, so omega belongs to pencil alpha beta, right? But is that saying that omega inverts alpha to beta? Wait, did they start with two arbitrary pencils?
We started with alpha and omega.
Alpha and omega, right?
We inverted omega in alpha to get beta.
Yeah, it belongs to the pencil alpha omega. Any two circles with
That is what it's saying. If we invert alpha and beta, we get omega. And vice versa.
yeah, I don't know. Since beta belongs to the pencil, omega belongs to the pencil alpha beta. So it seems like they've assumed that alpha and beta invert to each other.
Possibly. Wow.
Two non-intersecting or tangent circles are just one. Yeah, this is a little bit unclear. Can you see this was the statement we needed last time with the mid circles?
Yeah.
We'll get to that next, but what does that mean? Maybe the chat can help us.
Yes.
No, just nothing in the chat. Well, at least it seems like it's saying that we have enough progress to conclude that it happens, yeah?
Yeah.
So any two circles, alpha and beta, yeah? It's basically saying you can find the mid circle on its pencil, yeah? Yeah?
Oh.
But is it true?
Is it claiming that beta will be the mid-circle of alpha and omega? Is that the idea?
Oh. Since beta belongs.
Because this is like when the mid circle is
Yeah.
or is it that the negatives?
Beta. Oh, okay. It's not saying it's proved. Like it's saying we're ready to prove.
What?
There's an actual page here.
That's Greitzer.
It's like it's stylistic. It's fooled us stylistically. Okay, so if alpha and beta intersect, I guess we could have come up with this ourselves. It's just we were confused that it was already implied, which it clearly wasn't. Yeah, it was assumed. Okay, so if alpha and beta intersect, we can invert them into intersecting lines, which are transformed into each other by reflection either in their angle bisectors, in either of their angle bisectors. Inverting back again, we see that the intersecting circles have two mid-circles, orthogonal to each other and bisecting the angles between alpha and beta. Should I erase some stuff? Is it time? Let me erase this, yeah?
Yes.
Yeah.
It is.
Let's see if the time.
Okay, so if alpha and beta intersect, yeah?
Yeah.
This is alpha and beta. We can invert them into intersecting lines. So that means you've got to invert about one of these points.
That goes good.
Yeah. I think it's the only way because if you don't pick one of those points, they should turn into intersecting circles, right?
Oh yeah.
So invert about O, and then you get intersecting lines.
And then you have
P prime, yeah? Which are transformed into each other by reflection. So you can reflect here, yeah? Converting back again. Oh, okay, so they're saying reflect, yeah? So this is alpha prime, yeah? This is beta prime. And then we want to reflect it. So then beta prime is now equal to r of alpha prime, yeah?
So it's over the angle bisector.
Yeah.
And if we invert the angle bisector back, would that become the mid circle? Or one of the mid circles?
Okay, so if we invert back, we'll get back to these circles, right?
Yeah.
So these circles have now switched. Yeah? It's kind of like maybe we could have done that before with the lines instead of the circles. But then they were always circles. Anyway, so if you invert them back, okay,
So your angle bisector becomes the mid circle.
we see that the intersecting circles alpha and beta have two mid-circles, orthogonal to each other and bisecting the angles between alpha and beta. Oh. Oh. I don't think it actually says it very explicitly, but I think what it's trying to say is that the reflection is the inversion. Remember how we said reflection and inversion are related?
No.
Alright, anyway, but like, so is it possible that the angle bisectors, yeah, the black lines, are the mid-circles when you invert them back? That's what you said, right?
Or wouldn't that be key?
There's two of them, yeah? So there's at least one. It says when they're intersecting, there's two.
Yeah.
Yeah? So we need that fact. That's the fact we need. So
Oh.
any two inner circles have at least one mid-circle. If they intersect, there's two.
Oh.
And if they don't intersect or if they're tangent, there's one, yeah?
Yeah.
Okay, so we're saying... Wait, but does that make... Is it actually true, though? Is it obvious?
When they intersect where those two lines mean there's two angle bisectors. And I suppose that gives you two mid circles.
Yeah. So this... Oh, that's crazy. So inversion about this. See, this is basically the claim it made before, but maybe it's stated differently. So inversion about this line, about this circle, right, is reflection about this line.
Oh. Yeah,
That's the same thing.
Because this is a circle when it's inverted, yeah.
So reflection is the same as inversion.
sort of kind of.
Yeah.
When.
So this definitely reflects these lines to each other, right?
It's just like,
But is it obvious that the circle inverts the circles to each other? So the circle goes through P, right?
yeah.
And it has to go through O as well, yeah? So it has to go through like these, yeah?
Wait,
Yeah.
how can it be
To
two? Where's the second?
oh, it doesn't have to be the diameter. There could be like there's lots of circles going through. I don't actually know what it looks like.
Oh.
So maybe it's more like it could be like this. Yeah.
Yeah.
So if alpha and beta intersect, we convert them into intersecting lines which are transformed into each other by reflection in their angle bisectors. Inverting back again, we see that the intersecting circles have two mid-circles, orthogonal to each other, and bisecting the angles between alpha and beta.
That's their tangents.
Oh, okay. So these circles have to be orthogonal to each other, yeah?
Yeah.
And if it's an angle bisector, then they have to bisect the angles between the circles too.
Yeah.
So I guess if we wanted to be a bit more careful. Yeah, so you take the angles they meet the tangents, right? Yeah. Bisect them. Yeah. And that's how this tangent should meet the other two circles. So like
Because this is like on the left of here.
Maybe it's really huge. But... Oh, it's never gonna make it, is it?
Oh.
Um. Well, it's like this, yeah.
Yeah.
And there's another one like that, yeah.
Yeah. What does that? Oh yeah.
Is it obvious they invert into each other? La, la, la. Hmm. So those two circles are orthogonal to each other. Fixes that. Hmm. Oh, wait. If you have a circle, how many circles have the right, just the right angle with that circle, you know, in that pencil? So if the circles intersect, right? Like, if you have two circles and they intersect, so like it's clear that so the black circle, right? When you invert about this left black circle, it fixes the right black circle, yeah, because it's orthogonal, yeah. It also takes the left blue circle, yeah, to something that makes the same angle, yeah, because it preserves angles, right?
Yeah.
It makes the same angle with itself, yeah.
Oh yeah.
It has to be.
So it has to. Well, one thing that has the same angle with itself is the original circle, yeah. So it could preserve the circle by that, just that property, right? Or it sends it to another circle which has the same angle, right?
Yeah.
Of which beta is another one of those circles, yeah. Okay. And the question is, I mean, can you have how many angles can you have between these circles? I mean, the pencil is all the circles passing through those 2 points, yeah.
There's only one line, so I suppose I'm going to do it. So
Oh yeah.
I
Yeah.
don't know if that's really what like the four circles go to lines, up the vertical lines, and there's only one line.
Yeah.
Go over that circle, yeah.
Oh yeah.
Yeah, that's fine.
Yeah. I surprise
right.
myself sometimes.
There's a form that turned into something like
Okay, so why doesn't it turn it into itself?
because that's
What does it mean to turn it into itself? It has to be orthogonal, right?
It's not like or not. That's
Why is it not orthogonal?
done.
Wait, Haibing said something. I think you invert the angle bisector, and that gets you the mid-circle.
Yeah.
Oh, there is a bit of lag on the chat, I think.
10 minutes behind.
And then Sean says, oh, cool. Yeah, there was this thing about Elon Musk. He was saying, I don't know if I said this already, but like, he got into this conversation with, the Alibaba guy.
Yeah.
Yeah.
Yeah, so he's there talking and they don't know what to say. And so he's like, and then the Alibaba guy is like saying, oh, I never have afraid. He always say this weird thing. Like,
I saw the video.
Did you see it? Yeah, it was like, I'm never afraid of the artificial intelligence. The people cannot make something smarter than the people. Like, they're always saying stuff like this.
Yeah.
And then Elon Musk is like, all right, so we're talking, right? We're talking and we type. So our output is about like kilobytes per second. Yeah. So AI output when they communicate to each other at the moment could even be terabytes per second.
Yeah.
So we would just seem ridiculously stupid to them. Like, what would that be like? That'd be like us talking to a tree. We're just talking to a tree. It's like we're waiting for it to talk to us. It's not talking, Like terabytes per second versus kilobytes per second. I guess it came to my mind because they kind of have to type stuff.
Oh, yeah.
So there's like, I have to express my thoughts with
Yeah.
3 letters and so it's like, this is like bits per second, bits per hour. Okay, so we have a black circle. So the blue circles, can they be orthogonal to each other?
They can.
Wait, a circle can't be orthogonal. Wait, hold on.
If you're a formula, it's still fine, right? Because then it's not orthogonal to the angle bisector, which is 45 degrees.
Yeah.
The only way it can be
Yeah,
orthogonal to the black circle if it's like 180 with an end. I don't know if that's
Yeah. Okay, so alpha going to alpha would make this angle 90, right? In which case, right.
after going
So if alpha were to go to alpha, yeah,
the
you're saying basically like this angle would be 90. So that's 180, yeah? So alpha and beta are actually the same anyway, right?
oh yeah
Yeah?
yeah
So it can't be orthogonal, yeah? So alpha has to go somewhere else.
Yeah.
And then as you said, there's only one other thing that makes this the angle.
yeah
Because when you have a line, there's only 2 lines that make the angle.
yeah
Yeah, on either side. And it doesn't go to itself, so it has to go to the other one. Yeah, very good.
nice. So that's when they intersect.
So that's when they intersect. There's 2 mid-circles, yeah? The 2 black lines. 2 black circles, I mean. If alpha and beta are tangent, can you see the other cases that just pretty much realizing that there are other cases? Yeah, like, so alpha and beta are tangent, we can invert them into parallel lines. So what is that? So that's like if it was like this. Yeah?
What is that?
So if you want to invert them into parallel lines, right, then you have to invert about their point of tangency.
Yeah.
Because that's the only way to invert them into lines, right?
Yeah.
Okay.
Do we care about where the lines are?
Well, we know the lines are parallel because they can't intersect, right?
So just and then
So they're parallel, yeah? Oh, where would you put this inverting circle?
in the middle.
In the middle.
Whoa.
Okay, so then we have a unique mid-circle, yeah? So it's like the parallel line in between.
So you feel like because so this one's
Yeah, and so the parallel line in between. Wait, how does this justify? So you have a circle that's also tangent at that point, right? Actually, did we already prove a theorem about the reflecting? Then we'd save some trouble reasoning this. Does this actually say? It was actually a theorem, I think. Was there actually a theorem that said something about
Well, I think doesn't get the second because ours the second.
what?
I think that's pretty much in the chat.
Oh,
Ours the intersecting one thing.
which intersecting one?
It's probably one the same.
Oh, okay. So we now know it has to be the bisector circle, right?
Yeah.
So we take the bisector circle, the black circle, and we note that inversion preserves angles, yeah? So it makes a certain angle with alpha, okay? And we know that it makes the same angle with beta because it's the bisector, right? So it has to send alpha to something that makes the same angle. So and there's only two things that make the same angle. So it has to send alpha or to beta, yeah? And when it sends, are you in the chat yet?
I still have to, I haven't.
Okay, so we're basically saying there's only two things that make an angle, so it has to send to one of them, and it can't send it to itself because that would make the angle 180 degrees, so then they'd be equal, yeah? Because sending it to itself means it's orthogonal. Yeah. Alright, so where are we up to? Oh, there was this really cool comment about, I don't know if you remember this thing where like geometry is what you can construct with a straight edge and a compass. Remember that? So there was a theorem or something that said you can actually construct everything with just a compass. Without a straight edge.
Yeah, you can make any straight line into
Yeah, I guess I don't know exactly what it means, but like it seems like you can actually invert any straight line into a circle. Right? So then you can kind of, if you have a way of drawing, like if you have a way of constructing inversions of stuff without a ruler, then you can do everything, yeah? I think that's how it was proved. That's what it said in the book. It was like, yeah, I heard about that from somewhere else though. So it says it can be shown by inversion that all constructions with straight edge and compass can be done with compasses alone. Hudson. Oh no, okay. No, this is not Hudson. This is something else. It's in the references anyway. There was a bit that we did earlier that was like saying that, or maybe it was an exercise. It was like something about reflections. In this way, inversion can be considered reflections. Maybe this was with the projected plane or something. No, it's basically dinner time. Okay, so let's finish this off quickly and then we'll come back and review it if we need it. Okay, so if the tangent, then we know there's one, right? Should only be one. If they don't touch each other at all,
they make concentric circles.
oh, is that what happens?
Yeah, that's what it says happen. Invert them, concentric circles, these concentric circles.
Oh, then you can talk about a middle concentric circle.
Yeah.
Yeah. What's it say? So if they're non-intersecting, convert them into concentric circles of radii A and B. These concentric circles are transformed into each other by inversion in a concentric circle whose radius is the geometric mean. We did that at some point, remember? You can invert concentric circles to each other with something that's sort of in between them.
Oh, yeah.
You just write it down, yeah?
I suppose you can just use the definition for that.
Yeah, inverting back again, we
Somewhat,
see that non-intersecting circles, alpha and beta, have a unique mid-circle. If alpha and beta are congruent, then mid-circle coincides with their radical axis.
Congruent. It's in like
The same size.
Oh.
same size. Yeah.
Oh, so it's literally kind of identified like a line as a circle. A radical axis is considered a circle.
Exactly. Yes.
So when the circles are actually the same, the radical axis is the reflecting line, right? Oh, so if the circles are actually
Yeah.
the same, you can't invert them to each other with a circle.
Yeah.
Well, you just choose the invert circle to
A line.
itself. And so you invert them into concentric circles, and if their radii are the same, they're inverted by the same circle, then, essentially.
Oh, but that's
And then when you invert that back,
no, that I don't think that'll work
maybe not.
because if you had two circles of the same, right,
Yeah.
and you used one to invert the other, that other circle would just go inside.
Oh yeah, that's inside.
It goes inside, right?
Yeah.
So it's actually taking the radical axis.
Yeah.
Yeah. Okay. So we can see it's unique without necessarily seeing why it works, yeah?
Yeah.
Maybe we can come back to that.
Yeah.
We'll come back to that, yeah? Alright, we can end this massive video for like 2 hours. Alright, dinner time, people.